are going to be looking at detailing of slab, but as part of introduction, we are going to be considering how you can design slab. And to be able to do that, first you must be able to understand your drawing. What you are designing, you should be able to understand what you want to detail. Without a proper understanding of your drawing, you will not be able to detail. In this, our sample drawing today, let's look at it in detail, closely. Now, if we have a slab, first, from elementary drawing, when you have a dotted line, that means the line is hidden. So in this case, what we have here is an edge of our slab because it's continuous. So wherever it's continuous, you know you are seeing the edge of the slab. So in this case, we have, because it's a single line here, that means it is a cantilever. Please, in this edition of this training, it is assumed that you understand how to use an AutoCAD. So this is not intended to teach the use of AutoCAD, but in other trainings, we also have how you can use AutoCAD. So in this particular training, we are going to be applying the use of AutoCAD. So we assume you understand how to use AutoCAD. Okay, let's continue. So when you have the dotted lines here, that means both edges of the beams are hidden. And a situation where you have this is most likely to be a cantilever. So in this particular case, it is a cantilevered slab. So what that means is that after the beam, the slab will project a little bit. So this is a situation here, and the moment you have two lines crossing each other, what that means too is that there is a void. So at that particular place, you don't have a slab there. It's a void. So where we have here, this is a void, and this is what you use to represent a core wall in this kind of scenario. Okay, but that's not where our focus is now. So this is a typical case of first floor general arrangement. General arrangement drawings is where you have all your elements. General arrangement drawings show how your elements, the configurations of all your elements that make up the structure. So here we have our columns, the rectangular shape is column, and then what we have here is our beam. And in this case, this is our staircase and our core wall. That's the lift shaft. And it's also, in this case, in this class, this training class, we are not also teaching you the general arrangement. This you will find in other video. So we admonish you to follow us closely or to look out for other videos that will have on how to come up with a drawing like this, how to come up with a general arrangement. So here too, what this means is that we don't have any beam here, but between the wall there is something like a beam, or you can call it where you have the door of the lift shaft. Okay, so now we have different types of slab. We have a one-way slab, we have a two-way slab, and a one-way spanning slab means that the two edges are supported. Number one case, when the two edges are supported by beams or walls, but the other two edges are not supported, it is called a spanning wall. Is a one-way spanning slab. That is one scenario. The other scenario is when the longer side of the slab is divided by divided by the shorter side is more than 2. So if the coefficient or the factor is more than 2, our Ly over Ls factor is more than 2. That means it can be designed as a two-way slab, as a one-way slab, sorry. And also there are literatures which advise, and I think some codes as well, which advise that when the load on a slab is up to a particular value, you can equally ignore the Ly over Ls factor, the K factor. You can ignore it and do what? Ignore it and consider it as a two-way slab, irrespective of what the factor is. So, but in practical applications, oftentimes you might not start going into this, but this is also based on your engineering experience, your engineering decision making, the quality of your decision making. But in the end, everything boils down to you. Okay, so in this case, you want to look at it, each of the panel, to see when you have a one way is supported by 4 edges on the beams. That is one. And then your Ly, sorry, two ways slab. Then your Ly over Lx is less than 2. Is less than 2. So when it is less than 2, you can consider it as a two-way slab. And the other reason why you can equally consider it, like I said earlier, is when the load is beyond a particular limit. So now, let's look at when it is two-way slab, the edges conditions. You have to understand the edges condition to be able to design it properly. So in this slab here, the top left, we have an edge. Remember I told you before that if you have a line and a stretch, right here we are not having anything here. So that means at this point the edge is not continuous. So how do you determine this? When you measure your slab, sorry, let's go back to the model space. So we are going to be measuring, and you measure your slab from this way to this way. This is 4.5 meters. You measure this is 4050 millimeter. So when you divide this, of course, is our Ly, and this is our Lx. So when you divide your Ly by Lx, what do you have? You have a factor, a K factor that is less than 2, meaning we are going to be designing this as a two-way slab. So the next thing we need to determine is our edge conditions. So the edge conditions, the edge coefficient is what? Here, alongside there is what? Discontinuous. Also, an edge can be discontinuous when is the continuity of the slab is not up to half. Then they take it from half, but it's also advisable you leave it for more than half. So what I'm trying to say is that even though we have slab that is continuous on this edge, but because it's not even covering up to half, we can consider this as what? A discontinuous edge. So the shorter side, the shorter edge, the first edge, we can what? this is discontinuous, this is continuous because it's bounded by another slab. Okay, so let's continue. So like I said earlier, in this particular edition, we are going to be focusing on how we can design this. And there are many methods of the design of slab. The most popular is the yield line method, and whereby you use with the use of simple coefficient analysis. And then where you have irregular shapes, where you have maybe line load on a slab, it might be adequate to use finite element method, which consider discretization of the elements and then go on. Another thing you need to take note of when you are designing a slab, or even if you want to detail a slab, put it in your mind that the width you are going to be considering is 1 meter, 1 meter unit. So, and is also the same apply. It also applies to wall. So, when we have this, you can look at it as okay. You just take a portion of this. Like if you are considering your x direction, you just measure 1 meter. Your y direction is just 1 meter. So what it means is that when we want to detail this, or want to design this, this is our, from here to here is the width of our slab. That means our y direction, we are going to be detailing the reinforcement we'll get from our design. We are going to distribute it within this 1 meter. But because this is a sample, we can equally apply it. By the time we begin to do the design, you have a better understanding of this. Okay, now I've prepared an Excel sheet which I've used over my career span. Today I'm going to be sharing it with you, and those who may be interested in the PDF version of this, because it's well detailed, in order to be a guide when you choose to do your own, or you can use another way, another method of carrying out your analysis. Okay, so let's continue. Now, my cover page, I have the details, the title of this report, the client, the proposed project, the location, then consultants we have prepared by, which is still optional, and of course our logo is here. Then the design data. Now, for every design, you must have your design data, the project brief and the intended use of the project. Is it residential? Is it an office complex? Is it a workshop? Is it a foundry? Is it a factory? Because this will determine what the load you are going to be applying. And then you also talk of the relevant codes. We have different codes. In different countries, they have different codes that are approved. US, you have their code, Indians, Brazil, Turkey. But in Nigeria, the codes that are acceptable, we use BS codes, and then we use Euro codes. But in this design, we are going to be restricting ourselves to the use of BS code. So now, the relevant code, we have BS 8110 Part 1 1997, which is structural use of concrete. Then we have BS 6399 Part 1 1996, loading for building, code of practice for dead and imposed loads. Then we have BS 6399 Part 2 1997, which is loading for buildings, code for practice for wind load. Even though we are not going to be using this using wind load here for our design of slab, we are going to be restricting ourselves to only vertical load, vertical combinations. Okay, so you select your relevant codes. You have to determine that, and then you also have to determine your material data. And the first material you are going to determine is a concrete cube strength at 28 days. So, and this is covered in BS 8110 Part 1, 1997. Due to copyright issues, I may not be displaying some of this value here, but you can contact us to guide you on how you can get copies. So now, in selection of the material data, we are going to be doing as much as possible. We are going to be stating the part of the clause, and that's why I said when you watch this video, you can check out, when you have the copy, you can check out the clause that covers this. So now, in this case, we are going to be selecting using 25, and according to this clause, the minimum for every structural element is 30 Newton per millimeter square. That is grade 25. Grade 30, sorry. However, the code allows that due to difficulties of getting the strength, especially where you have issue with getting quality constituent materials, maybe the quality of sand, materials, the components of the constituent material to make concrete, where it is difficult, you can reduce it for up to 25, which is the minimum. But you need to use your judgment very well, especially if you are in this part of the world. It's very difficult to attain this 25 Newton per millimeter square. So you have to be very careful when you select this, and this is for your durability consideration. So you also have, since we are not going to be dealing with staircase here, we are going to leave it at the 25. Then for reinforcement, now in Nigeria we have it as 410, even though where you have some products that are even more than 500, and some codes allow for more than 500. However, you have to also be very careful if you are in this part of the world, because in the markets, I can tell you from experience, we have different reinforcement in the market that you cannot even lay your hand on the mechanical properties of this thing. So you have to be sure what you are specifying here, they will be able to get it. So if you are specifying 500 Newton per millimeter square as the tensile strength, you have to be sure they will be able to get it. Then the next thing is for you to determine the concrete cover to reinforcement, and this is covered in BS 110 Part 1, 1997, Clause 3.3. Everything you need to know there, which tells you about the exposure condition. And in Table 2, you have the mild condition, you have the severe condition, and even very severe, moderate, and very, very severe. So you have different conditions. So you must determine this slab, how exposed is it? Is it exposed to water? Is it exposed to aggressive condition? Is it exposed to severe condition? But in this case, we are going to assume that is exposed to mild condition. So when you determine that, the mild condition, now the next thing you are going to determine is, okay, since steel is not does not perform so well when subjected to fire how many hours do you want the slab to be able to withstand fire. So in this case, we are going to be using 1 hour. Or you can even say, okay, for 1.5 hours, that you are still very okay. So that means whenever it's subjected to fire, whenever there is fire incident, your design should be able to, your structure should be able to withstand up to 1.5 hours. Okay, and this is contained in table 3.4 of this same class. Then you now talk of the cover, the nominal cover, and then considering the the exposure condition, which will specify if it is mild, what is the how many millimeter, the size of the cover, then the fire resistance if it's 0.5, if it's 1.5, if it's 1 hour, 2 hours, 3 hours, the codes will also specify. So then you talk of the nominal cover, which should now be able to give you at least the maximum size of the aggregate you are going to be using. So in this particular case, we are going to be looking at 25 mm as a cover. And this is very important. So with this, we'll be able to withstand up to 1.5 millimeter, 1.5 hour of fire resistance, and equally, because it's a mild condition, even 20 mm is still okay. So now we go back to our drawing to find out from what we determined before. We said it is a two-way slab, and because of that, I am going to be using a two-way slab I prepared before, and this is my own way of reporting, of doing my analysis. So I have the drawing shown here. Okay, so go now panel 1, which is this panel. I said you must panel all your drawing, all your layout to see panel 1, panel 2, panel 3, and that will show, is it a one-way slab, is it a two-way slab, then is it a cantilevered slab like what we have here, and then the next thing you are going to be looking at is also the thickness. And you have to pay attention to the thickness, because in some scenarios, this could be 150 millimeter, and then when you get to the next panel, it is higher or even lower. But in this case, it's going to be 150 all through. And this can even change by the time you carry out your design. Because is more or less like our constitution as engineers, so you must be able to understand the relevant provisions in code, which is what will determine the decision you make, the minimum decision. It must satisfy it. So I can't just come here and say, okay, I'm designing this slab to 10 Newton per millimeter square. It will not go through approval. It must meet the minimum standard, the minimum value approved. So equally here, whereas this slab, whereas maybe 75, assuming 75 is able to withstand, pass your analysis, will it be accepted? The code must determine what you can use. Okay, so let's proceed. So I've prepared this before, so I'm going to be running through to explain. So here we have the width, which is what I explained earlier when it comes to a two-way slab. Even the design of a slab, the width, because the code provides that you carry out the design as though it is a beam. So you have some provisions of the beams that you follow. Then in addition, you have some other extra provisions that covers for solid slab. So in this case, we have already determined our preliminary size, which is subject to change if it doesn't pass condition. Then our size we say is 4.05. Then the ly, which is the long side, is 4.50. Let's confirm that again. So, and this can change, meaning if we are paneling this, whereas this is our long edge here, if we come to design this panel, what are we going to be having? This is 5 meters. So then we'll now measure this, the full edge of the slab. So in this case now, the table has turned. That means from grid line 4E to 5E, it will become our short end. So please, you must pay attention to this. So the next thing, you see, our factors have been determined, and because it's 1.11, that means it's a two-way slab. It's less than 2 K factor. So our covers that we just predetermined is 25 mm. Then our finishes, which can be seen in units of construction materials, which you have to determine. All these can be gotten from different literature and even the relevant code. For instance, you have this, you have different unit of concrete and mortar. You can see hardened normal concrete, reinforced. So these are not things you pick from your head, even though with experience over time you might have some of these values. But you need to know what are the materials that are going to be used, and then what are the units weight to enable you calculate whatever you are going to be having. Okay, you can see even that of block is all, they are all taken here. So you can see plaster, what finishes both sides. So if you want to even take the 0.6 times 2, you can equally say okay, 1.2. So please, you need to, okay, assuming it's 25 mm our floor finish, you can see minimum thick terrazzo floor 0.5, this terrazzo paving 6 mm. So you must determine the finishing, and that will give you the load here, which is 1.2, in this case 1.2 kilonewton per meter square. All this you must determine what the actual value is, so that you will not under design your slab. Then you can make provision for partition allowance. This is also optional, but I think the code specifies that you make this. Then our concrete value, which we put the minimum strength here, and then our tensile strength, say 4.3. Then our life load, which is covered by relevant provisions of the codes of the loading for building. Please, on table 1, you see the various factors. For an office complex, it recommends 2.5, but as a principle, I am making it 3, just to have an adequate provision. So the next thing we are going to check here is the edge conditions. Now, first, we take the general data, the loading information. Then the next is our support conditions and load cases. And this is very, very vital, because in most tables, you come about this. This is how you pick your coefficient, your moment coefficient that will be used to carry out your design. So, in this case, The short edges, let's look at the short edges of our slab. So on the left side is what? Is continuous. Is discontinuous. That is not continuing. We don't have slab after this edge. But going to the right side, we have slab after the edge. So what that now means is that here we have just a 2 edge which we can uh, specify as one. Only one edge is continuous. For the long span, let's look at it again. So in this case, this edge, there is no slab. This edge, because the slab here is not up to 50 or 70% that I explained earlier, we are going to consider it as a discontinuous edge. So we'll say 0. And the load case now will be what? The slab is continuous only over one short edge. The other 3 edges are discontinuous. And this can change depending on its factors. In this kind of cases where all the edges are discontinuous, it makes it an exterior span. So, but in this our example, we have it, assuming it is 1 1, meaning the short and the long one's edges continuous, it will be, the load case will be load case 4. But in this particular instance of the slab, is only one edge that is continuous. And that we have, so here the short edge, one is continuous, the other one is discontinuous. For this, we have it as discontinuous edge. Okay, so both edge discontinuous, one. Okay, just to have appropriately, we do continuous. Discontinuous edge. So, and on this side we have continuous edge. See, continuous edge. Okay. So I think this settles it. So this is very, very vital. You can't play with this because from the coefficient table, we have this as this is used to determine our coefficient value. So you must state it clearly. So now, what are the uses of all this information? That's the next thing we'll go. So in the calculation of the loading, what are the loads coming on the slab? So the first, number 1, is your self-weight. So the self-weight here, the self-weight is now 24 times the thickness of the slab. From the unit weight just now, you said materials per area, we have for concrete, the unit weight for concrete is, okay, for concrete is, okay, hardened concrete is 25. It is also allowed because it's reinforced, or fresh concrete usually. You can also consider it as 25. But now I am going to be considering it as 24. So 24, which is a unit weight of the concrete times the thickness, will give you 3.6. And this, I mean, this is 1.75. It will also change to 4.2. But we are starting with 0.15. So let's revert. So then the partition allowance, the finishes, which we have already determined this, then the partition allowance, and this make up your dead load, or what you call the permanent actions. And what it means is that these loads do not change, they are permanent. So they are dead loads, they are there as permanent load. So you have, maybe you have your block wall on a slab is permanent. But in your house where you could have your center table, your chairs which you can move up and down, you can't consider that as dead load. But those features or those constructions, those features that are permanent, you can't shift them during the course of usage of your structure. You can't move the block wall. Today you put it on left hand side, tomorrow you put no. So all these are permanent. So you have to group the dead load together. So in this case we add 3.6 plus 1.2 plus 1, which will give us 5.8. Then we now talk of the life load, which is the imposed load, life actions, variable actions, because they can change. If it's office 2.5 according to BS, as I explained earlier, if it's residential 1.5 and other, but you don't even need to take it from your head. Check this table, you see where you check to see where your structure fall under the intended use of the structure. Then we also talk of the resultant factored uniform load, and this is where you apply the factor of safety. And according to the standard, we will use 1.4 for the dead load, and then 1.5, 1.6 for the life load. For other codes like the Euro code, this could be 1.35, and this could be this factor of safety, partial factor of safety, could be 1.5. But for BS is 1.4, which we multiply by the dead load, then plus 1.6, which we multiply by the life load, and this will give the distributed load, the uniformly distributed load on the slab. So in this case, we have it as 12.9. When you multiply this and add this with this, you have it as 12.92 kilonewton per meter square. But because we are considering a meter weight, we will now make it per meter run. So it becomes 12.92 kilonewton per meter run. So for every 1 meter, we have the distributed load as 12.92. So the next thing we are now going to go into, because it's a two-way slab, meaning we have to consider the short span, that is the span between here and here, that's between E and D. You must consider the span. Calculate the bending moment, the maximum bending moment, which you now use for your design in the short direction. And then you also need to do that for your long direction. So, and both the long and the short, first you must check for the span, moment, then the support, depending on the support condition. If it is continuous, then you must analyze for the design of the support or the edge condition. Now, whether it is continuous, whether it is simply supported or not, whether there is moment or not, you must still make provision for the minimum reinforcement, but we will go into that. So for the short span, your LX, the bending moment and reinforcement, this is covered by BS 8110 Part 1 1997 Clause 3.5 Clause 3.53. So, and this gives you the table where from where you have to now determine what your beta is for the x, the span in x direction. So, but I've also tried to automate this, and I'm going to give you a clue. Sorry, let me delete this. Now, so the moment coefficient table, I've automated this using the formula because how they generated this table, they are out there in the code in this class. So I use it to generate the table. So it becomes automated, meaning like in this case where we have 0.55, if the k factor changes, assuming this is 1, that value will change. This has been analyzed. It's automated, but I advise you to check how you can determine this. So, and this makes the process very easy for me to detail my slab. Because in less than 5 minutes, in less than 3 minutes, I'm done designing my slab. Okay, so, but we'll go through one by one. So, in this table now, we have the BS, that's for the beta, the factor for the long span and the long edges. We have it. Then for the short edge, because this is given, in this particular case, the B2, because the short edge, one of the short edges is discontinuous, meaning the factor there is 0. So we have your R, so which is also calculated, is provided there, and then your BS, your beta XX, the short span, which you are considering right now to be this value. So from here, we determine the coefficient value to be 0.055. I have explained how you can get this. Like I said, for copyright issues, I may not be able to open the table here, but we have all the tables we can provide if you request for it, comment, request for it. Okay, now, so our moment for the span, our maximum bending moment will be L times L square times the coefficient, and your W, which we calculated earlier as a load, a distributed load, times the span, the short span, which is 4.05. So that will give us mx. So this becomes our moment that we are going to be using for the design. So the next thing is to assume our diameter. You can assume, you can even start from 10. But the codes in some places also specify the minimum you can use. And I think Y10 is actually acceptable. But in this part of the world too, I will also recommend you don't go below Y12 for some obvious reasons, except where you are sure of the mechanical properties of the materials and you are sure they will meet the requirement, the minimum requirement. And then for approval purposes too, there are authorities like the development controls in Abuja, the ones in charge in Lagos and wherever you may be, they all have their specification as well. So this is our width, which we said earlier that is going to be 1 meter, and then the effective depth, which is our depth minus the cover minus the assumed diameter over 2. So in this case, our depth is 150 minus, all these are automated. So you see, are covered by formula. So whatever we have here, we have provided earlier is what we are going to be having. So if I change this to 0.2, this way I don't need to come here and begin to change it. So it's automatic. And that is why it's very precise. 0.15. Please, this is for my personal use, but the steps are there one by one with the formula, detailed formula. So if you want it, I can give you the PDF version which can enable you to do. But I know most of us can do analysis of slab. And there are a lot of literatures that cover this as well. So now we have this 150 minus this and equals to 112 as the effective depth. Then, and this changes with reinforcement. If we use 10, that means it increases here equally. But we're going to be using our assumed diameter as 12. So then, the moment factor, which we must test it against the ultimate moment of resistance of the concrete, which is M prime, and the factor is usually pegged at 0.156. What this means is that if your K, which is your design moment over the concrete strength multiplied by the width multiplied by the depth squared, if it is more or equal to 0.15, if it's more than 0.156, what it means now is that you must design that section as a W reinforced concrete. Let me show you. Assuming we just make this 0.75, it's just to test it. What I'm saying, you can see the factor here is more than 0.156, and that is what it means is that you have to design this section as doubly reinforced section, and this is not advisable for a solid slab. No, it's not advisable. It's not economical to design, because the moment you are getting to this point, you begin to require shear reinforcement and all of that. So you want to avoid it. You can see. So this is how the K factor works. So in this case, but like I said, I only tested it. So we revert back to 1.5 and then we'll get back to it. Sorry, all those conditions are predetermined to alert me whenever I am, going beyond bounds. So in this case, our K is equals to 0.033, which we'll now use to calculate our lever arm. And the lever arm is the definition, or how do I put it? The formula here is your depth, your effective depth, which you have calculated, multiplied by summation of 0.5 plus square root of 0.25 minus K over 9, which also must be less or equal to 0.95D. So some may even go straight to select their lever arm, take the maximum value and use 0.95D. So meaning they multiply this by what? 0.9. But that is very conservative for you to be using 0.95D. But if you are using manual calculations and you don't want to start going into, you can equally assume that. And so when you do that, you arrive as your lever arm being 114.49. So you now use your lever arm to calculate your area of reinforcement. So the area of reinforcement, mind you, we are doing for mid-span. I've explained that before. Your span reinforcement. Okay. So your AS will be equal to the design moment over 0.95, and these are all specified by the code. This formula, you obtain all this formula from the code. So for another code, it might be slightly different. For Euro code, it might be slightly different. But for BS, this is what you have. So we have it as 0.95 multiplied by the tensile strength of the reinforcement multiplied by the uh, lever arm, which is our 114. We have it here, 114.49, which you can even say 115. So now, by the time you use it to define, to multiply, what it means is that you have the area required as, and you do this calculation, the area required is 261 millimeters square. Let's go back to explain this. So we are, in this case, this is our short span. So we are going to be assuming we want to detail this. Please, I'm just drawing this line. This is not how we detail. We'll still go back to it. So for our bottom reinforcement, what it means is that within this 1 meter run from this point to this point, the area you must supply there must not be less than 261 millimeters square. That is what that calculation is saying. So it's not all through the slab. So within that 1 meter, the total area of reinforcement must not be less than 261. And another thing is that you must test it. You must test this to ensure that you are providing a minimum reinforcement. So for every section, because even without application of load, every section generates moment, which is called moment of resistance, which you must counter it. And that is why codes provide that there must be a minimum reinforcement. So assuming our area here, let's say, is just 100 millimeters square. Is it 100 am I going to provide? No. I will now have to go back to check what the minimum reinforcement is. And in this case is automated, but the codes, BS code, provide that the minimum reinforcement must not be less than 0.16% of the area of the concrete. So this is what it means. Sorry, let's go back. So now, if the section in this case is 1.5, let's see, 150, then we go to 1 meter. Okay. So what it's saying is that the area, this 1 meter by, that's the width, which is 1 meter by 0.15 meter. That's 150. That the area, let's see, 0.15 times, let's put it in tens of millimeter, 150 millimeter times 1000, which is the width. This is the area of the section, which is 150 millimeter, 150,000 millimeters square. And what the code is saying is that it must not be less than, in this case, 1 of this section. So what it's saying is, yes, whatever area you are having there, it cannot be less than this minimum. And I want to believe that that is clear. So the area, the minimum area is A, which is AC, the area of the concrete of that particular section. So meaning if it is 200, it will change. If the area of that section is 300, it will change. So in this case, what it's saying is that this area, you must have it as 0.16% of this area. So 0.16% of the area. So please, you have to check the code you are using, what is the relevant provision, and then you'll be good. So let's go on. So what we now, since the area calculated here is more than this, so we are okay, sorry, it's more than this 261. So the next thing where a lot of people struggle to understand is that the area you are going to provide for the bottom reinforcement for this section must not be less than 261. And how do you generate this? Yes, in a lot of tables you will get these values, but it's always very important to do what? It's very important to understand the basic principle. How do you generate this? So if we have the area, now let's say it's 12, this is 12 millimeter, right? I'm going to have it. I'm taking my time because after this stage, we are going to be moving on. So what it's saying is that you first calculate for one bar of 12 mm, what is the area? Pi r square. Let me correct myself. So if the diameter is 12 here, what it means is that we say pi. So with Excel, you can automate this. So plus pi r square, we type P, I. You see pi. Press your tab key, and then you close it. Multiply by r square, which is what? This divided by 2, right? Then times this divided by 2. So you can do the square as well by saying, okay, put this in bracket, which is another option of representing this. So the area is 113, sorry, not 226, like I said earlier. So you can equally put this, maybe if you prefer using the square. So here, you press exponential 2. So from here, if you have 10, this is the area 78. If you have 16, this is the area 201. So, but in this case, we have 12. So what this is saying is that between here, just one bar is giving you 113. And from your calculations, your 261 is already sufficient. Meaning, how many bars will give you this value? How many bars? So here, we would divide what we have here. In this case now, let's say it's 261. We divide it by, let me use equal so that I don't get confused. If you divide equal to 261, divide by this. So it's telling you that you can use 2.3 of Y12. So what it's saying now is that between here and here, I need a minimum of 4 bars, right? So these 4 bars I need to space them, isn't it? And the spacing, if we have 1 meter, this is 1 meter, and I'm putting 4 bars here, what will be the spacing? So it's not so complex, it's just a matter of understanding. So now, for a 1 meter, now it's already determined, sorry, 3 bars, not 4, 2.3. So I'm approximating it to 3. So what he's saying is that between here and here, I need to have 3 bars, which you can equally say, okay, from here, right? In this case, you can easily put this. So by calculation, this reinforcement is sufficient to take care of this section. With emphasis, I say by calculation. See, so it means that the spacing in this case, which ordinarily you are supposed to specify, will be 488 millimeter millimeter spacing. But the code will go ahead to limit the spacing to say, see, yes, maybe from your calculation, you're having 500, you're having, maybe it's even just 2 bars that can work here, meaning it's 500, but it will limit it to say, okay, in as much as you're having this spacing, you cannot go for more than so. So, depending on the code you are using, you have to what? Determine what is the limiting factors. And as a matter of principle, personally, I have limited my spacing to be what? To be 250 millimeters. So, irrespective of the bar size I'm using, the moment the area is satisfied, I will not go for below 250. Sorry, for more than 250. So when you do this, so in this case, I am going to provide 250. So meaning when I'm detailing this bar, I am going to provide this. I'll go to say, okay, between this, I'm going to go for 250. So I'll come 250. The next is 500. The next is 750. And then I go back. So with this, what do you now have? So within this unit, you will now have how many bars? 1, 2, 3, 4, 5. Meaning within this meter, you have, within this area, you are not specifying the number of bars anymore. You are not saying, oh, provide 5 Y12. For a group of bars that is usually specified when you are talking about slab or area or walls, you talk of the spacing. So in this case, I am going to now say, okay, provide Y12 at 250 millimeters. So, and by the time you provide that at 250 millimeters, you multiply, let's see the area to give us. In this case, what we are saying is that now we have how many spacing? So we have 1, 2, 3, 4. So, and this is with what? 5 bars. So if we check within this 1 unit, 5 times this. So this will be the area. Or you can even be conservative to say, okay, no, it's 4. And which will be 452. Meaning, within this area, you have, even though from your calculation, you have what is required is 261 millimeter square, but you are now providing a 452 millimeter square for every 1 meter. For every 1 meter. So between here and here, what you are saying is that you are providing this, even though we are using 5 in between. And this is how your reinforcement is determined. And whatever we have done there is also similar for the support. So we now go and for the support that is continuous, one edge is not continuous. So we'll now check that, because both of these edges, let's check our slab. What we are saying is that because the edge, the long span here, which is bounding the short direction, because this edge is not continuous. This edge is not continuous. For your short direction, your short span, the moment here is assumed to be 0. The moment here is assumed to be 0. So in that case, you will now make provision when you are doing your detail. You make provision providing minimum reinforcement, or in some cases where based on containment, the code will provide what you are going to be using. So whatever we have done here, you now switch to the long span. It's still similar thing you are going to be doing. Nothing else is changing. So you follow through, and then just the same way. And when you are done with that, you check for your deflection, which will check the effect at serviceability limit state, the effect when the structure is put to use. So this in itself does not pose so much integrity issue. However, you wouldn't want to come and see you wouldn't want to see crack. You wouldn't want to see some level of deflection. So because of that, you must also check for deflection, which is also provided for under BS 8110, Chapter 1, 1997, Clause 3.57. So, and there you see the design stress to be Fs, which is 2/3 of times the reinforcement you are providing times the area required over area provided. And when you have that, you check modification factor, which you use to modify, and the formula is there, which is for 0.55 plus, into bracket 477 minus fx, into this, divide by this, and then you limit it to 2. It cannot be more than 2. So if you have, after analyzing this, assuming it's 2.5, you have to limit it. You have to pick 2. So when you do in this case, based on analysis, it's 2.1. So we use the modification factor to be 2. So the allowable span depth ratio will now be what? 20, which is also specified in the code, depending on the support condition. Is it continuous? Is it this? In this particular case, the modification factor is 20. So, sorry, is yes, it's 20. That's the allowable span depth ratio, 20 multiplied by the multiplication factor, which is 40. So there are tables, even like some literatures, that provide this. Depending on the code you are using, this may be calculated differently. This may also be specified differently. Then what is now your actual span? So if you multiply this, your actual span, the allowable span depth ratio is saying must not be more than 40. So what you have here is the actual, which is 4,000, that's 4.5 meters, 4.05 meters, which is 4,050 millimeter divided by the effective depth. Remember when we calculated the effective depth? Here well, for our short span 119. So we have it. So with this, you see that it is less than 40, and because it's less than 40, the deflection is satisfied to be okay. So meaning your analysis is okay. So for this particular slab, you are now going to be in this direction. You are going to be providing Y12 at 250 millimeter spacing. And this is where we are going to be stopping. In the next edition, we will now be looking at how you can detail. That's it for the bottom and also for the slab. So that is where you will now be able to check how you can detail this particular portion. So you can equally do that for what we have done. You can equally do that for all the other panels. And then for cantilever slab, that you can also have a way of analyzing that, which please you may have to find out. I also have the template for it, but for want of times, maybe at another time, I am going to be doing that in another section. So you can also look out for that.